Hello, my name is Jana Bektas. I'm a research assistant at the Communication Networks Institute of the Technical University of Dortmund in Germany, and I will now present you a work entitled Rapid Network Planning of Temporary Private 5G Networks with Unsupervised Machine Learning in the course of the IEEE VTC 2021 Fall Conference. My presentation is structured as follows. First, I will clarify the question why private 5G networks are important and why in this context automated network planning is necessary. Then I will explain the requirements of automated network planning and present our developed framework. I will then go on to the evaluation of the framework and finally close the presentation with a conclusion and an outlook to future work. So why is the topic of private 5G networks so important? In various countries all around the world, it is now possible to use 5G spectrum in the context of private use. The spectrum usage licenses of these so-called private 5G networks are usually awarded to companies after an application has been submitted to the relevant authorities. We observe that especially in Germany, there are already more than 150 local frequency assignments, and we expect this trend to go on in other countries too. The next question is, why do we need private 5G networks? Private 5G networks are seen as key enablers for customized communication solutions. For example, guaranteed quality of service is enabled because the assigned frequency spectrum resources are granted exclusively, in contrast to technologies like Wi-Fi in the 2.4 GHz band, where interferences are common. Additionally, fully digitized environments can be deployed safely for industrial applications and critical infrastructures. Also, ad hoc and temporary deployments are made possible where quality of service requirements in the context of fast deployment and rapidly changing local conditions can't be met with traditional static mobile communication networks. Examples for such applications are public major events like sports events or concerts, rapidly varying logistics or emergency situations where digitally assisted temporary hospitals are required. The major drawback of private 5G networks are that hard regulations regarding antenna placement and interference, as well as the fact that applications with high quality of service requirements are deployed, are existent. So, communication network planning is required, in contrast to simple Wi-Fi networks, which is a challenge for stakeholders without any communication networks expertise. One solution to this problem is rapid and automated network planning, which is the topic of this presentation. I will now present you our solution for automated and rapid network planning based on unsupervised machine learning and start with its requirements. So what are the requirements for automated and rapid network planning? Firstly, it must be easily usable because the users will probably not have any communication networks knowledge. This means that the whole network planning process must be automated, for example, using machine learning methods. Secondly, the network planning must be reasonably fast in order to enable temporary ad hoc deployments. In order to utilize machine learning for this process, the databases must be well-founded. For example, existing professional radio field calculation software must be applicable. Of course, modularity is another useful feature which enables the use of different radio field calculation models as well as other machine learning models. In order to meet all these requirements, we propose following automated network planning framework which we developed and evaluated. The automated network planning is conducted following a set of planning phases. The first phase is called input and initialization, where a site boundary polygon and a target mean power and coverage goal are defined by the user. These are the only inputs required by the user of the framework to meet the easy-to-use criterion. Then, all environment data, including buildings, is downloaded from OpenStreetMap and then converted to a format usable by the well-known ray tracing software WinProp, which is utilized by our network planning framework. After that, the environment is prepared for the radio field simulations. First, an internal scenario model is created. In this process, the scenario map is enlarged to incorporate possible reflections from outside the site and in order to be able to check compliance with regulatory restrictions. Then, possible antenna positions are identified. In this case, building centroids on the rooftops of buildings with a pre-configured minimal height of 5 meters are chosen. After preparation of the environment, so-called radio environmental maps or REMs are calculated with the ray tracing software WinProp. This is done for every antenna position with different equivalent isotropically radiated power levels, or EIRPs, and the results are converted to the internal scenario model in order to be usable by the machine learning model. In this case, we use omnidirectional antennas only. Subsequently, all results violating the boundary power restriction of minus 80 dBm are filtered from the dataset. This is based on the rules of the German Federal Network Agency. The filtered results will not be used by the machine learning model in order to speed up the learning process. In the next and final phase, the unsupervised learning or clustering-based antenna placement is prepared and carried out. The filtered results are transformed into a result space usable by the clustering method. For this, the RAMs are transformed into polygons containing all areas where the received power is greater than the target power. By doing this, we obtain many different polygons, which are reminiscent of puzzle pieces that are to be put together by the clustering method to form as large an area as possible, thus obtaining the greatest coverage possible with the target received power. To do this, the centroids of all these RAM polygons are calculated. These centroids are then clustered using the k-means clustering method. After that, we can choose the base station in each cluster which produces the biggest sum area and thus the highest sum coverage, leading to a network planning solution comprising antenna positions and utilize EIRPs. The number of clusters is thus equivalent to the number of utilized base stations. In the upcoming slides, I will present the simulation scenario and the corresponding evaluation results in order to verify the functionality of our framework. The simulation scenario and the corresponding evaluation results will be explained based on the processing steps of the automated network planning, which I described earlier. So on the first step, the site boundary polygon is defined, which is the city of Monaco in this case, depicted by the teal-colored polygon on the city map. Based on this overall scenario, two more polygons are defined, representing different temporary events. A Formula 1 race scenario, which is held within the city area, and a sailing regatta, which is carried out in the harbor area. For all three of these scenarios, only the RAMs of the overall city must be simulated once. For the adaptations for the different scenarios, only the prioritized area is changed within the clustering-based coverage planning model. The next step is to identify possible antenna positions, which are depicted here as positions on buildings higher than 5 meters. After that, all these antenna positions are used for the radio field simulations in WinProp to create a viable databases for machine learning. As already mentioned, results violating regulatory restrictions are filtered. Two of these results are depicted here as examples. The detailed simulation parameters of the WinProp software can be found in the paper. After all simulations are done and the databases is generated, the next step is to transform the result space into the supposed puzzle pieces. Here we see these areas in the form of white polygons with black borders and the corresponding centroids of these polygons, which are used to cluster the results. As an example, the results for 2 clusters and 3 and 4 clusters are depicted here, where the different colors represent different clusters. It can be seen that a good geometric separation can be achieved with the k-means clustering method. On this slide, I want to show some example network planning results for the target power of minus 90 dBm. Note that power outside of the private network borders does not exceed minus 80 dBm. Also, the white spots are obstacles like buildings and do not affect the coverage calculations. The first example is the overall city area, where the color heat map represents the received power in dBm, the red border describes the prioritized area, and the purple hexagon depicts base stations locations. It can be observed that the clustering method has distributed the base stations spatially separated, thus achieving almost 95% coverage with the target power. This also complies with the regulatory restriction that a maximum of minus 80 dBm power is present outside the city borders. Of course, this could be optimized with sector antennas, which I will later address in the conclusion. The next example result is the Formula 1 scenario where the pre-calculated and filtered RAMs are used by the clustering method to prioritize the given area. Here, 3 base stations are enough to achieve roughly 97% of coverage. Again, the clustering method behaves reasonably and distributes the base stations exactly along the racetrack. A similar result is achieved in the sailing regatta, where 2 base stations are required to cover roughly 95% of the harbor area. Here, the overall coverage ratio of all 3 scenarios is depicted over the number of clusters, which also represent the number of base stations. As you can see, the coverage of the F1 scenario is saturated at 3 base stations. Moreover, it can be observed that while the sailing area is easily covered, the overall city area needs at least 7 base stations to get similar performance. This makes sense, as the sailing area is mostly free space attenuation, while the city area is more densely covered by buildings. The F1 scenario in turn represents an in-between of the 2 scenarios, and thus the number of base stations required for similar coverage is in the middle of the other 2 scenarios. On this slide, the time for calculation is plotted against the number of clusters or base stations for all 3 scenarios. Additionally, the one-time simulation duration of the radio environmental maps is depicted as a dashed line. Note that this calculation occurs one time only and is not repeated between the network planning of all 3 scenarios, as the databases for all scenarios is the same. Although the RAM calculations can take up to 48 hours dependent on model detail, the pre-calculated RAMs enable rapid network planning for temporary purposes in minutes, as can be seen on the plots for all 3 scenarios. In order to round up my presentation, I will conclude with a summary and an outlook to future work. In this work, we developed an automated and rapid network planning framework for private 5G networks, which integrates a complex 3D ray tracing-based radio field simulator and implements a clustering-based approach for automated 5G coverage planning. We then evaluated the framework based on a realistic scenario with changing conditions due to temporary events, where we show that the target network planning solutions can be met while being confronted with restrictions, for example regulations, and temporary deployments or adaptations can be calculated within minutes. In conclusion, premise owners who plan to deploy private 5G networks are effectively supported by our system in terms of coverage network planning. For future work, we plan to extend the automated network framework with more antenna types like sector or beamforming antennas, which are planned to be strongly involved in 5G deployments, with sector or beam alignment planning based on, for example, reinforcement learning, capacity planning, including the planning of network slices, and inclusion of own ray tracing or other possibly machine learning based radio field simulation concepts. This concludes my presentations, so thank you very much for your attention. For further questions, you can contact me via email, and for more information on the chair's other scientific activities, you can check out our website or our YouTube channel. Goodbye.